Hi, my name is Sam Albert. Today I'm presenting our work, Maneuver Design and Flight Control for a Martian Probe Network. This was completed along with my advisor and co-author, Dr. Hans-Peter Schaub. So to start with some high-level motivation for this problem, let's start somewhere familiar. This is the entry, descent, and landing timeline for the Mars 2020 mission, also known as the 7 minutes of terror. It's called that because this is a string of highly complex mission critical events, and each of those subsystems has its own risk associated with it. So to have an acceptable overall probability of success, the risk from each of those subsystems has to be driven down in some way. So let's take a look specifically at the parachute deployment. So for the Mars 2020 supersonic parachute, some of the specific risk reduction activities included a lot of modeling and simulation, leading into hardware testing, in this case, flight test on a sounding rocket. And that eventually culminated in successful supersonic parachute deployment on Mars. There's this incredible video looking up at the real thing. You know, it's probably not recorded very well here, but YouTube it. And the point though of this slide is that each of these risk reduction activities takes substantial engineering effort, and that takes time and it costs money. So what if I claimed that there's a way to dramatically reduce the risk and cost to the mission from the parachute subsystem? So to substantially reduce both might sound too good to be true, but it's possible if you eliminate the parachute subsystem. And so, you know, I say that in a bit of a joking way, but that's sort of the line of thinking of something like SHIELD, or the Small High Impact Energy Landing Device. It's a vehicle concept under development at NASA JPL. And the idea here is to minimize complexity, in part by eliminating subsystems wherever possible, to design what's the simplest landing device that we can imagine, and how can we then find science missions that would be appropriate for such a platform. So this is a small, mostly passive ballistic rough lander for Mars. Ballistic meaning it doesn't exert any lift during flight, rough meaning it has substantial impact deceleration loads. It only has 2 events during EDL. It deploys a drag skirt once it goes subsonic, and we'll talk more about that later, and it eventually jettisons its heat shield. It also relies on crushable material to attenuate the final impact deceleration. And so with this, it's designed with a 5-kilogram payload in mind, and is targeting about roughly 1,000 Earth Gs at landing. This might sound pretty familiar to another mission, and the Mars microprobes specifically. So just to go ahead and draw that comparison, the Mars microprobes were 3.6 kilograms per probe, and they had about an order of magnitude more deceleration on impact, in the ballpark of 30,000 Earth Gs. So that's sort of the comparison between these two ideas. But you know, why would we go in this direction when we've shown that we can land something as large and complex as the Perseverance rover on Mars? Well, part of it is the context that Mars sample return is the top priority at Mars for the next decade. It'll cost in the range of $4 billion across multiple missions, and it is extremely exciting. But there's also, you know, a lot of science at Mars that we're interested in that's not addressed by Mars sample return. And because of this, there's a community of scientists and engineers interested in identifying low-cost science missions that would enable us to continue a regular mission cadence during and after Mars sample return. This is evidenced by some recent studies, including one from the Keck Institute for Space Studies with the cover shown on the right, as well as a recent workshop. And the Keck Institute study in particular identified networks of small rough landers as a promising mission architecture for these type of low-cost missions. In the topics of atmospheric science and seismology were especially good fits in terms of science investigations. Furthermore, if we could co-deliver all of these passive probes to their entry trajectories from a single carrier spacecraft, we could further reduce complexity compared to probes that have to maneuver in space or delivering them on, you know, multiple spacecraft. So all of this taken together motivates a study of maneuver design and uncertainty quantification for the co-delivery of a network of passive ballistic probes. And that's the subject of the talk today. So before we get to talking about networks themselves, I'll quickly go through a flight mechanics analysis of just a single SHIELD probe at a time. It begins with entry 6 kilometers per second at the interface of 125 kilometers. And for most of SHIELD's EDL, it's stored in its aeroshell, completely passive. By the time it gets subsonic, we want the Mach number to be below 0.9, and then it deploys this drag skirt. The purpose here is really just to further reduce the terminal velocity of the probe such that it lands with a lower speed. Sometime later, it needs to get rid of its heat shield, and then it lands and is targeting an impact speed below 50 meters per second. So for these 3 identified nominal entry flight path angles, or EFPAs, we can then constrain the acceptable timing of these events based on the Mach requirement and the impact velocity requirement, and then identify nominal timing in that range. And so this is showing that timeline for an EFPA of -18 degrees. And then we performed an uncertainty analysis to see, when we apply these relevant uncertainties, will the probes still meet the requirements when it's just triggered based on time? It's not actually identifying when it goes subsonic during flight. So this histogram is showing the Mach number at drag skirt deploy for each of the entry flight path angles. Takeaway here is just that none of these dispersed cases really even get close to going above 0.9. I'm not showing a histogram for impact velocity because there's so little variation. It's basically a straight column. That's because even though there's variation in the trajectory earlier on, by the time it gets through these EDL events, it always eventually gets onto that terminal velocity curve. So as long as the events happen early enough for that to occur, there's very little variation in impact velocity. It's at about 44 or 45 meters per second. So that requirement is met as well. And then we're also showing landing error here. This is with respect to the, between the dispersed landing and the nominal landing site. So as one would expect, as the entry flight path angle gets steeper, the landing dispersions go down. What's interesting here is that there's a huge reduction from -12 to -18, but then the returns sort of diminish as you go from -18 to -24, for example. There's only sort of an incremental improvement there. So the conclusion we can draw here is that a simple timer that kicks off when deceleration exceeds some threshold is sufficient to command shields EDL events within these assumed requirements. I'll also just quickly mention that we took a look at using this subsonic drag skirt deployment to achieve control, but because that occurs so late in the trajectory, almost all of the energy has already been dissipated, and you can only get maybe plus or minus 3 kilometers of control authority. That's really not nearly enough to moderate the expected downrange error. So the drag skirt deployment is not intelligently timed for control, but the fact that you can do it just from a simple timer eliminates the, as opposed to, for example, a range trigger or a velocity trigger, might eliminate other hardware or flight software requirements you would otherwise need. And so this is just a further way to minimize complexity. Okay, so now we're going to turn to networks, and specifically regional networks of these probes. And to state the assumptions of this study, we're looking at shield probes with the aerodynamics just described. And the main assumption here is that precision landing is not a priority. We can precisely position them after they land, but they don't need to go to exact landing sites. What's important is that the network is delivered to basically the right spot on the Martian surface, and that the network retains its desired distribution and shape approximately. If we can spread it out in the desired way, it doesn't have to get exactly on the landing sites that we identified. We also assume that these probes are all co-delivered by a single carrier spacecraft that is already on an entry trajectory. Then the probes separate from that carrier mechanically. So these aren't propulsive delta Vs, they're what we're thinking of as spring jettisons, for example. And these jettison events occur within 20 days of entry. For this regional network study, we're going to assume an entry flight path angle of -12 degrees. And lastly, in addition to these dispersions shown earlier, we're now also dispersing jettison speed with a uniform distribution at plus or minus 10% of its nominal value. So in cases where the separation on the surface that we're looking for is pretty small, we can take advantage of sort of a local neighborhood and the approximately linear relationship that occurs between the required jettison velocity and our desired change in landing site coordinates, latitude and longitude. We can set up the Jacobian, numerically evaluate it, invert it, or in this case, it's not square, so we take the least norm solution. We can then solve for the required jettison velocity given a desired change in landing site. And this linearization works pretty well for separations that are less than about 100 kilometers. And that's shown here with error on the y-axis and the desired separation on the x-axis. But then you can see that after about 100 kilometers, the error grows and then begins to, this method rapidly degrades. So you have to stay within that area for the linearized targeting. So we use that method to design maneuvers for this notional network of 6 probes. The idea here is a regional seismic network delivered to Cerberus Fossae, a region of known seismicity on Mars. And so the nominal landing sites are shown in the orange stars here. And then the results of a 1,000 trial Monte Carlo analysis are shown with these blue dots. These are substantial landing dispersions, and one might naively look at this and think that there will be all kinds of network distortion as a result of those dispersions, but it turns out, most of this error is strongly correlated between the different probes. The error in jettison velocity is independent for each probe, and that will affect them all differently. But the dispersions on entry flight path angle and entry velocity of the approach trajectory, as well as on density, atmospheric density, more or less just shifts the network around back and forth in the downrange direction specifically. So in this case, we quantified the distortion of the network shape and chose the worst case scenario, and that's shown in these red pentagons, sort of just look like red dots. And just from visual inspection, you can see it mostly just took the same shape and shifted it in downrange. It is distorted some, but clearly it's basically the right shape. It's still delivered to the Cerberus Fossae region on Mars. And so under the assumptions that we stated, where we don't so much care about precision landing, we've shown that this type of passive targeting for a regional network of probes on Mars, that they can be co-delivered with this passive targeting technique. But what if we want networks that are larger in extent than about 100 kilometers? So we've looked at that as well. Instead of the linearized targeting method, we just use a numerical nonlinear optimizer on the problem. And we're going to go through first some of the sort of trade study results here, or parametric relationships. So on this slide, we are varying the timing of separation, always for cross-track separation on the surface, with an entry flight path angle of the approach trajectory of -18 degrees. So on the left, you can see these 2 different curves. This is desired separation versus required jettison speed. And you can see that this orange curve, which is separation 3 days out, takes a lot higher jettison speeds and also increases a lot faster than the results if you separate 18 days before entry. So as one would expect, you require much lower jettison speeds to get the same separation distances. And as a result, we were also able to get solutions going much further out. And then if you imagine a curve connecting these leftmost points, that's what's shown on the right in effect. So this is always for 5 degrees desired separation. And now we're varying that separation time. So you can see, indeed, as you increase the time before entry where separation occurs, the required jettison speed goes down in this sort of nonlinear fashion where it looks like it's starting to asymptote out as you get further and further back from entry for that separation. Now in this slide, we're looking at along track separations on the left and cross track separations on the right. And we're always separating 3 days before entry in this case. And we're looking at, again, the required jettison speed versus the desired separation distance. And on the right, for cross-track, first of all, we have basically no impact by changing the entry flight path angle of that approach trajectory. And we also see what is actually roughly a linear increase in jettison speed with desired separation. So this is sort of close to what we might expect. On the left, first of all, in this case, the jettison speeds have been normalized to show that the shape of these curves is very similar. But it is important to note that they are significantly offset as a result of the different entry flight path angles of their approach trajectory. Furthermore, for a while, the jettison speed that's required increases as every time you increase the desired separation, but then it really plateaus out after about maybe 15, 20 degrees separation, maybe 1,000, 1,500 kilometers separation, in other words. And after that point, very small changes in jettison speed create very large separations on the surface. And so we'll get to it in a minute why that's a problem. But because that's a little bit counterintuitive, let's look at the trajectories themselves that we're generating for these along track separations, or in other words, they're extending further and further in the downrange direction. So we're showing altitude versus downrange here, and we're showing to scale in the inertial frame here, kind of looking down at the plane of motion. We can see that for the first few trajectories, they're just incrementally offset. They're getting a little shallower in entry flight path angle for the probe itself. And then after a while, they're coming in on a very similar trajectory, but due to tiny changes, they coast longer and longer during the atmospheric flight phase, to the point that these final couple trajectories actually skip out of the atmosphere and then finally come back in over their desired landing site. And you would see that if we zoomed in really close on this figure. So they're achieving these long extensions by flying through the atmosphere for a long time, and that's part of why these jettison speeds change so little. And we did an uncertainty quantification using another 1,000-trial Monte Carlo analysis, and saw, as we'll talk through here, indeed that makes them highly sensitive to error. So in this case, we're separating 3 days before entry, looking at the performance of 4 different along track separations with increasing distances. And the first 3 perform all right. I mean, 200 kilometers of error is certainly not great, but at least that's bounded, and it's increasing incrementally. And then you get these huge dispersions for this 4th case that's targeting about 25 degrees of separation. Almost a third of the cases miss the planet entirely for this scenario, and close to 60% of them have larger than 500 kilometers in error. So this is just is terrible performance for this probe's targeting. The reason for this can be gleaned from looking at the plot on the right, where we're showing the entry flight path angle of the probe itself for each of these desired separations. And so it is getting shallower and shallower, and it's also getting more and more spread out. So a lot of variation in a shallow entry flight path angle combined with this long coast time in the atmosphere is what leads to this really high sensitivity to error for these generated trajectories. Let's look at the same results for our cross-track separations. Again, 4 different cases with increasing separation distances. Somewhat similar trend where these are more incremental increases, and then really large dispersions for this 4th case, targeting in this case about 30 degrees of separation. It is better. None of them are higher than 500 kilometers in error, much less missing the planet. And we could sort of understand this behavior again by looking at the entry flight path angles of the probes. For these cross-track separations, they're all nominally at about negative 18 degrees, the entry flight path angle of the carrier spacecraft. But as the maneuvers become larger, and I forgot to mention that for cross-track, we're separating 18 days before entry, so much further ahead of time. And as the maneuvers get larger and we're really far ahead of time, that leads to significant entry flight path angle dispersions, as shown here. And that's what leads to this really large landing error. Another interesting difference here shows up when we look at, okay, well, what if the jettison velocity is performed perfectly? Remove the maneuver dispersions and everything else is kept the same, perform another Monte Carlo analysis. And then we'll look at the long track results on the left. No cases are missing the planet. This is significantly better. And for the first 3, this is starting to be what maybe we would call acceptable. 40 kilometers is still large, but that's close to what we saw earlier for the regional probe. But then we still have a much larger dispersion for this 4th case. And what I wanted to emphasize here is that it's not just that the maneuvers are performed imperfectly, or that the maneuvers themselves are larger. This trajectory is just inherently much more sensitive to error as a result of its path through the atmosphere. In contrast, we can look at the cross-track separations. And in this case, they all collapse to basically the same performance and all have a good performance. This looks consistent with what we saw with a single probe analysis. And what's going on here is that for the cross-track, most of that large error was coming from performing a sizable maneuver far ahead of time and doing so imperfectly. So when that's performed just right, still have some dispersions that are coming from the relatively small errors that we introduced in the approach trajectory and the atmosphere dispersions. But by and large, it's not as inherently sensitive to error as these long track extensions are, as a result of the different ways that these trajectories fly through the atmosphere. So quickly, we'll walk through conclusions of this study. Hopefully, I've convinced you that co-delivery of a network of small rough landers is a promising architecture for low-cost Mars missions. Under the assumptions we made in this study, SHIELD has ample margin to rely on a timer triggered by deceleration for EDL events, for commanding EDL events. Within about 100 kilometers, maneuver design is roughly linear and probes can be co-delivered to a consistent network shape. then in the range from about 100 to about 1,000 kilometers, in other words, up to about 15 degrees in separation, maneuver design is nonlinear, but the probes can still be passively delivered to the network with rough accuracy. And then above that separation, the trajectories we generated here really just become too sensitive for passive targeting to be realistic. There are certainly other approaches, though. One would be to, in some way, drive down that expected maneuver execution error. We assumed a relatively large dispersion here for that. You could also allow the carrier spacecraft to perform multiple maneuvers during approach. You could also allow separation from the probes earlier than 20 days before entry. Of course, if you permit multiple carrier spacecraft, then you can just deliver these probes exactly where they need to go. Not necessarily one for each probe, but several bunches could make this problem much easier. And finally, when optimizing to find these trajectories, one could programmatically avoid these long atmospheric coast phases and constrain the range of the entry flight path angles available to the probes. That might result in higher jettison speeds, but trajectories that aren't so highly sensitive to air, like the ones that we showed here. Okay, so if you have any questions, please feel free to email me. If you'll be at the AAS Astrodynamics conference in person, please come say hello. Thanks for watching.